Look at example 4. Find the Fourier series for fx equals negative x in the range of -1 to 1 and fx plus 2 equals to the fx. Okay, so the first thing you may want to highlight this part. You might want to look at this part. So whenever you see fx plus 2 equals fx, so it means the given function is a periodic function. Okay, if you can recall, in general, the function is a periodic function if ft plus capital T equals to ft. Okay, so the same thing here. Fx plus 2 equals to the fx, okay, where the t here denote the period. So in this case, we know that our period is 2. Or the 2 here is actually also can be seen from the given interval here, okay? Because basically if we sketch our diagram, then the interval is from -1 and 1 here. So somewhere here is 0, the origin. So we can see that the length, okay, from here to here is actually 2. So that's the period, okay, the length of our interval. All right. So now we can proceed. So the first step is to determine the capital T and L. So T equals 2 in this case, and then L is given by T over 2, which is 2 over 2 is 1. Okay, or the L here also can be seen from here because in general it is negative L to L. Right? So, and then second step is to draw the graph. Okay, this is optional. The second step here is actually to identify what type of fx that we have here. Okay, so we want to know whether fx is odd, even, or neither, so that we can identify which formula that we need to use. Okay, among these three, okay, which one that we need to use. So the second step here is to basically to know what type of function that we have. Okay, so again, to know what type of function, we can either draw, okay, to see the symmetrical property, or we can use the mathematical rule. Okay, so in this case, let us draw. Because sometimes in the exam, the questions start with the sketching of the graph first. Okay, so now, okay, so take x from -1 to 1 first. Okay, and then the graph is the function here is f, and the y-axis is your f. So fx equals -x. Okay, so I'm going to write here. So fx equals -x. Okay, so see, if x equals -1, if x equals -1, then your fx is going to be negative to the -1. This is your f. Okay, which is 1. So when x is -1, the f is 1. So somewhere here is 1. So this is the point that we should have. Okay, so similarly, if x equals 1, okay, so basically you test on the interval here. So when x equals 1, then your f is negative to the 1. So it's -1. So f equals -1 is somewhere here. So the corresponding nodes is here. When x is 1, so the point is and the f is -1. So we know that fx equals -x is a straight line. Okay, so we can just connect these two. Okay, so it's supposed to be passing through the origin somewhere here. Because if x is 0, then obviously your f is also 0. Okay, so this is your fx in the interval of -1 to 1. But we know that this is a periodic function. Periodic means the shape of the graph will be repeated, okay, in the next period. Okay, so in the next period, it's supposed to be, okay, if we consider at the right hand side, so the next period would be from 1 to 3 because the period is 2, the length is 2. Okay, so the next would be 1, the middle is 2, and then the right side is 3. Okay, so the shape, the line will be repeated. Okay, so this is the left and this is the right. Now in the second period here, in the right side here, this point here is going to be the left and this is going to be the right. Okay, so on the left it is here, on the right it's supposed to be down here. Okay, and then it's passing through the middle point. Okay, so we have this line. Okay, so you can see the line is repeated in the next period. Similarly, on the left, so we have -1. Okay, so to the left, it is supposed to be -3. Okay, because the period is 2. So somewhere here is -2, and here is supposed to be -3. Okay, so now this node is considered the left, and here the -1 here is considered the right point. So on the left it should be at the top, so somewhere here, and on the right it's supposed to be at the bottom at -1, and then we connect the line. Okay, okay. So basically if we expand more, okay, we will have the lines, okay, the similar pattern. Okay, but in the exam just enough if you expand one on the right and one more on the left. All right, so now based on the graph here, we can check whether fx is even or odd function or neither. Okay, so look at the symmetrical property of this graph here. So check whether it is symmetry on the y-axis or symmetry about the origin. Okay, so this one, what do you think? It is symmetry about the origin, because this point here, okay, this point here is reflected to this node. So it is symmetry about the origin. This node here, okay, is reflected to this one here. So it is symmetry about the origin. It is not symmetry about the y-axis. If it is symmetry about the y-axis, then this line here are supposed to be here as well. Okay, so for this one, it is odd function. Fx is odd. Okay, because it is symmetry about the origin. So if fx is odd, then the corresponding formula would be formula 3. So you go back to the formula 3, okay, check what do you need to compute. Okay, so next step is to calculate the Fourier series. Okay, so the formula 3 says that the Fourier series is given by only fx equals the summation of bn sine n pi x, because if fx is the odd, then a naught and an are automatically 0. So in this case, you just need to compute the bn, where in the formula, you can see bn is given by 2 over L, integral from 0 to L, fx sine n pi x over L dx. Okay, so this whole thing here is basically the element of the sine. Okay, so now we need to compute the bn. So bn is 2 over L. So in this case, in this problem, we know that our L is 1. So we have 2 over 1. So 2 integral from 0 to L. So L is 1. Fx is negative x given by the problem. So this is fx times sine, okay, so look here, n pi x over L. So we have n pi x over 1. So sine n pi x dx. So we need to solve that integral. Okay, so next step is to think of what is the technique of the integral that we need to apply here. Okay, so I can take out the -1 so that we have x sine n pi x only. Okay, so for this one, the technique is actually the tabular or the biparts. Okay, so for the tabular, we have positive, we have the x, and we have the sine n pi x. Okay, change the notation, so negative. So the second column we need to differentiate. So differentiate x is 1, integrate sine is negative, negative cos n pi x, but don't forget to differentiate n pi x respect to x, so we have n pi. Okay, and then proceed further until the second column is 0. Differentiate 1 is 0, integrate cos, so we have negative sine n pi x over n pi, so we have n square pi square. Okay, so the result would be -2, okay, so put things together, plus x negative. So we have negative x cos n pi x over n pi plus, okay, sine n pi x over n square pi square, evaluate from 0 to 1. Okay, so now when x is 1, okay, when x is 1, so we have -2, -1 cos n pi over n pi plus sine n pi over n square pi square. Okay, so this is when x equals 1, minus with a, so we have x equal to 0. So this is 0. The first part will be 0. Plus with a sine n pi x. So x is 0. So sine 0 is basically 0. So we have that. Okay. So we now have okay, cos n pi. So -2 and negative. So we have +2 cos n pi over n pi plus, sorry, this is -2 sine n pi over n square pi square. Okay, we have remarks here. Sine n pi equal to 0, cos n pi equals -1 power of n. Okay, here's the justification. Okay, sine n pi is always 0. See, n takes the positive integer. So when n equals 1, you can see you have sine pi. So this is 0. When n equals 2, you have sine 2 pi. This is 0. N equals 3, you have sine 3 pi. So this is also 0. So if you proceed, okay, for any value of n, you will get sine which is 0. Okay, so you can conclude that sine n pi is always 0 provided that n is positive integer. Okay, if n equals half, for example, then it's not true. Okay, so in the context of Fourier series, n is always positive integer. So sine n pi is always 0, but cos n pi can be simplified as -1 power of n. Here's the justification. When n equals 1, we have cos pi. Okay, so cos pi is -1. When n equals 2, we have cos 2 pi, which is +1. When n equals 3, we have cos 3 pi. This is -1. So if we proceed further, we have cos 4 pi, which is +1. So the pattern here, basically the sign positive and negative alternate. So this is actually can be simplified as -1 power of n, where n actually start from 1. Okay, so it is not true here. So n is from 1 up to any number of n, positive integer. Okay, so sine n pi is always 0. So basically this part is 0. And cos n pi is -1 power of n. So we have, so this is again our bn. So this is 2 over n pi, and the cos is -1 power of n. So that's our bn. So with that bn, we need to go back to this fx, the Fourier series. So we just rewrite the bn that we obtained. So we have here, so fx equals 2 over pi, because we have here 2 over pi n. So basically your fx, it is the summation n from 1 up to positive infinity, bn. So bn is 2 times -1 power of n over n pi sine n pi x. So sine n pi x. So in general, it is sine n pi x over L, but since our L is 1, so that's why we have sine n pi x only. So here you can put aside 2 over pi, before the summation notation, because in the summation here only for the n, the terms that involve the n. So the 2 over pi can be put aside here. So in the summation, we have -1 power of n over n sine n pi x. This n here cannot be put aside, because it is part of the summation that we have here. N equals 1 up to positive infinity. So the Fourier series of this function, the Fourier series of this fx here is given by this expression here. Right? So that's the example 4. Look at the next example. Second example, example 5. Given fx now in terms of piecewise function. Before this we only have one function fx. Now we have two functions. Based on different interval. So fx equals -x in the range of -pi to 0, and fx equals x in the range of 0 to pi. And given fx plus 2 pi equals the fx, so we know that the period, the capital T, is 2 pi in this case. So first of all, let us write the capital T is 2 pi, and the L is 2 pi over 2, which is pi. So then we draw our graph. So look carefully at this sketching here. So we have the axis first. Look at our interval. So the first one is -pi. So somewhere here is -pi. And here of course is 0. So now in the first interval, it is -x. So our fx equals -x in the first interval. So we test for x equals -pi. So we know that fx equals -x is a straight line. Y equals -x. But we want to know in which direction. The line. So x equals -pi, then our f is going to be negative to the -pi. So we have positive pi. So somewhere here is our f, so f equals pi is here. So when x equals negative pi, the f is pi. So this is the note that we should have. And then on the right interval, x equal to 0, then the f would be negative x equal to 0, so negative 0, so f equal to 0, so f is 0 is the at the origin. Okay, so we have two nodes here, so we just connect these two. Okay, that's for the first interval. Now on the second interval, we have fx equals x. So similarly, we test by looking at this the interval. So when x equal to 0 in the second interval, our f then is going to be 0. So on the right side, we have 0 to pi. So somewhere here, x equals pi. So when x is 0, f is 0. So we have again at the origin here. And then when x equals pi at the right interval, the f is positive pi. Okay, f equals pi. So when x is pi, the f is also pi. So we have this node over there. And then we connect the line. Okay, so that's the shape of our graph. Okay, in the range of negative pi to pi. Okay, so we can see that the graph is symmetry about the y-axis. So we know straight away this is the even function. Okay, but first of all, let us see the expansion of our graph. Okay, so on the right hand side here, the next expansion would be from pi to 3 pi, because the length of the interval should be 2 pi, the period of 2 pi. So we have at the right side, it is pi, so 2 pi somewhere here, and the next one is 3 pi. Okay, so we will repeat the shape of our graph in the next period. Okay, so we have this V shape here. So now the node, the x equals pi will be the left interval, the 3 pi will be the right interval. Okay, so we repeat the same shape. So we have like that. Okay, should touch this one. Similarly, on the left hand side, we have negative 2 pi and negative 3 pi. Okay, so the period is from here to here, from here to here, and from here to here. All of them is 2 pi, 2 pi, and 2 pi. Okay, so on the left here, so the shape of the graph would be start from here, goes down at the middle point, and then goes up to pi. Okay, so that's our graph. So we can see from the graph, fx is an even function. Fx is the even function because it is symmetry about y-axis. So when it is even function, then the formula would be formula number 2. Okay, so based on formula number 2, this is the Fourier series. Okay, for formula number 2, f(x) is equals to a naught over 2 plus the summation an cos n pi x over L. So we need to compute two things, a naught and an. So a naught in general is 2 over L integral from 0 to L fx dx. Okay, and an in general is 2 over L integral from 0 to L fx cos n pi x over L dx. All right, so we have here 2 over L. Our L is what? L is pi just now. So we have 2 over pi integral from 0 to L, 0 to pi. Fx is x dx. Okay, so 2 over pi, 0 to pi, x dx. Okay, so Okay, so you may want to look at this fx here. So this x here. Okay, in general, it is fx. So in this case, we have two function of fx. Okay, but the integral is from 0 to L, 0 to pi, 0 to pi. So that's why we choose x rather than negative x. Okay, but in this part, you can also choose, okay, can also use, if you prefer, you also can use from negative pi to 0, but the function would be negative x dx. Okay, because the idea is to take half part. Okay, but normally we are more comfortable to do the computation on the positive side. Okay, so we have 0 to pi x dx. Okay, so this is just a straightforward integral. So we have 2 over pi x squared over 2, evaluate from 0 to pi. So cut the story short, at the end we'll get pi. Okay. So you may want to work out on your own over there. And then we compute for the an. An is given by 2 over L. So we have 2 over pi, integral from 0 to L, so 0 to pi. So fx here, again, we consider x rather than negative x. Okay? So x cos n pi x over L. So our L here is pi, so we can cancel out with the pi at the top. So what's left is just cos n x dx. Okay, so again, the technique to solve that integral is again so I can just put here, this is the tabular or by parts. Okay, so I hope you can attempt on your own. So I just put the solution here. So 2 over pi. So by the tabular or by parts, then the solution would be x sine nx over n plus cos nx over n square. So we evaluate from 0 to pi. Okay, so we have 2 over pi. So when x is pi, so we have pi sine n pi over n plus cos n pi over n square. Okay, this is when x equals to pi, minus when x equal to 0, so the first term is 0, plus cos nx. Okay, here. Okay, when x equal to 0, so this part is 0, plus cos nx. Okay, so x is 0, so we have cos 0. Cos 0 is 1, so 1 over n square. All right. So again, we know that this cos n pi can be simplified as negative 1 power of n, and sine n pi is always 0. Okay, so simplify. So we have 2 over pi. Okay, so in the bracket we have negative 1 power of n over n square minus 1 over n square. Right. Okay, which can be written as 2 over n square pi. Okay, negative 1 power of n minus 1. Okay, right? So that's our en. So now put things together. So we need to go back to this fx. So put things together here. So we put the a naught and en. Okay, so therefore the Fourier series for fx is given by fx equals, so a naught over 2. So our a naught just now is pi. So pi over 2. Okay, so look back. this fx is a naught over 2. Okay, so we have pi over 2 plus the summation of n from 1 up to positive infinity, and then the an. So an is 2 over n square pi square. Okay, negative 1 power of n minus 1. Okay, multiply with the cos n pi x over L. So we have cos n pi x over L. Our L is pi. So again, we can simplify this one. Okay, so at the last, we can touch up a bit. So plus, so 2 over pi square can be put aside. Okay, so in the summation, we have 1 over n square. Okay, negative 1 power of n minus 1 multiply with the cos nx. Okay, so that's the Fourier series of the given function fx. Okay, so look for one more example. So hopefully you can understand this one. So the idea is to be able to identify which formula to be used. Okay, and then after that, just follow the formula for the a naught, an, or bn. Okay, and then at the end you just solve the integral. Okay, so after that you just put things together back in the fx. All right. Example 7, we have fx equals to the x and also 0. And then given fx plus 2 pi equals fx. So first of all, from the given function, we know that the period, the t is 2 pi, and then L is 2 pi over 2, so L is pi. Okay, and then we draw the graph. Okay, draw the graph of fx to see what kind of fx that we have. Either even, not, or neither. Okay, so first look at the first interval. So we have from negative pi to 0. Okay, and the next will be from 0 to pi. Okay, so the first function is x. Okay, so fx equals x in the range of negative pi to 0. So we check for when x equals to the negative pi, then the f will be negative pi, of course. Okay, so f equals negative pi should be at the bottom. So somewhere here is negative pi. Okay, the value of f. So we have pair of negative pi and negative pi. So the node will be here. So basically from here, we have negative pi and negative pi. When x equal to 0, so the right interval, so we have f equals to x, so x equal to 0. So the pair would be 0, 0. So we have one more here. Okay, so we know that this is a line, so we just connect these two nodes. So we have straight line over there. And then for the second interval, okay, for the second interval, we have fx equal to 0 in the range of 0 to pi. Okay, so this is straightforward. So we can see from 0 to pi, the f is 0. So basically this line. Okay, so we have this line and also this line. Okay, to be our initial initial graph. So if we expand at the right hand side, okay, so we know that at the right hand side it should start with the pi. So the next the right interval should be 3 pi because the period is 2 pi. Okay, the length of the interval is 2 pi. Okay, in between it should be 2 pi. Okay, so based on this given initial curve here, so now for this the expansion, so we need to start from here, okay, because at the left part it will start from here, okay, goes up to the middle and then goes to the right. Okay, so basically we repeat the same shape. So similarly at the left hand side, so in the middle it should be negative 2 pi, at the left it should be negative 2 pi. So at the left it should start at the bottom, goes up to the middle, and then okay, goes to the right. Okay, so that's our graph. So we can see from the graph, it is neither case, because it is not symmetry about the origin. It is also not symmetry about the y-axis. Okay, so for this case, this is neither. Okay, so this one. So if it is not odd, okay, it is not even, then the corresponding formula would be formula 1. So we have the full range here. Okay, so full means we need to compute the A naught, AN, and BN. Okay, so look at the first one. First of all, the Fourier series formula for Formula 1 is given here. Okay, so you can refer to the formula number 1. Okay, so we have A naught, AN, and BN to be computed. So first of all, let us compute the A naught. A naught is given by 1 over L. So refer to the formula 1. So it is from negative L to L in general, fx dx. Okay, but for this one, for this example, our fx is divided into 2. Okay, divided into 2 interval. Okay, so we have here our L is pi, so 1 over pi. So the interval should be 2. The first one is from negative pi to 0, and then the fx in that range is x. Okay, and then for the second interval, it is from 0 to pi, but the function is 0. So basically, we can ignore the second interval. So this is 0. So what we compute is just 1 over pi, and then the integral of x is x squared over 2. We evaluate from negative pi to 0. So simplify things here and there, we will get negative pi over 2. So this is our A naught. Later on, A naught will be put here. All right. And then the AN. So AN in general is given by 1 over L, integral from negative L to L, fx cos and pi x over L dx. Okay, so what we are going to have is then 1 over pi. Okay, again, the integral should be divided into 2. The first one is negative pi to 0. Fx is x in that interval times the cos. So our L is pi. Okay, so this is pi. So we always can cancel out with the pi at the top. So we have cos and x only. Dx, okay, plus the second one should be from 0 to pi, but the function here is 0. When you multiply with the cos, this is all 0, so we can ignore that part. So what we need to solve is just 1 over pi integral from negative pi to 0 x cos and x dx. So again, this is tabular or by parts, okay? So work out on that one. So I just give you the answer here. So 1 over pi. So the solution to the by using the by parts of tabular is given by x over n sine nx, okay, plus 1 over n square cos nx. Okay, we evaluate this one from negative pi to 0. Okay, so we have here 1 over pi. Okay, so see, when x is 0, the term here, so the term here will be 0. Okay, x is 0. So we have 0 over here plus 1 over n squared cos nx. So x is 0, we have cos 0. Cos 0 is 1, so what's left is just 1 over n squared. Okay, minus, so this is when x equal to 0, minus with the, now x equals negative pi, so we have negative pi over n sine n negative pi. Okay, plus 1 over n squared cos n negative pi. All right. And we should know that the property of even and odd function. So we have sine negative x is negative to the sine x, the property of odd function. And then the property of even function, cos negative x is equal to the positive of cos x. Okay, you can prove on your own based on the property of even and even and odd. So what it means by that property, okay, so this sine n negative pi basically can be written as negative to the sine n pi, and this one, okay, as well. So we can write that part to be negative sine n pi. And the cos part will be equal to the cos n pi. Okay, so what we have is then equals 1 over pi. So in the bracket, we have 1 over n squared, okay, minus pi sine n pi over n, minus, okay, because the negative here, okay, and then the positive over there. So minus 1 over n squared cos n pi. All right, and we know that the cos n pi can be simplified as negative 1 power of n, and sine n pi is always 0. Okay, so what's left now is 1 over pi, 1 over n squared minus negative 1 power of n over n squared, which can be written as 1 over pi n squared 1 minus negative 1 power of n. Okay, so that's our a n. Okay, now for the bn, so bn is given by 1 over L integral from negative L to L fx sine n pi x over L dx. Okay, so what we have is 1 over pi. Okay, again, we have from negative pi to 0. Fx in that interval is x, so sine n x, because our L is pi. Okay, so dx. And plus with the 0 to pi, but this one the fx is 0, so times the sine, so basically we can ignore that part. Okay, so what's left is just 1 over pi integral from negative pi to 0 x sine and x dx. Okay, so again this is tabular and also can be solved by parts. Right? So cut the story short. So this is what you're supposed to get. 1 over pi negative x over n cos nx plus 1 over n squared sine nx. Okay, you evaluate from negative pi to 0. Okay, so I hope you can do the evaluation. So to get at the end, you will get negative 1 over n, negative 1 power of n. Okay, which can be written as negative 1 power of n plus 1 over n. Okay, by the index property, because this is negative 1 power of 1 and this is negative 1 power of n. So by the index, we can write as n plus 1. Okay, so that's our bn. So finally, the Fourier series then can be written as fx equals to the, okay, so go back to this one. So this is the whole thing here. So we put back the A naught, A n, and B n. Okay, so the first one is a naught over 2. Our a naught just now is negative pi over 2. So we have negative pi over 2 over 2. So we have negative pi over 4. Okay, plus the summation of n equals 1 up to positive infinity. So we have an. Okay, so an is 1 minus negative 1 power of n over n square pi. Okay, so we need to multiply with the cos n pi x over L. Our L is pi, so what's left is just cos n x plus the Bn. So Bn is negative 1 n plus 1 over n multiply with the sine n pi x over L. So what's left is just sine nx. Okay, so everything here is in the summation term. So that's the Fourier series, okay, for the function given in example 7. Okay, so this is full range. Full range means you need to evaluate a naught, a n, b n. Okay, all of them. Okay, and the integral is slightly different because you have the full range. Okay, negative L to L. All right, so that's all for Fourier series. Okay, so for 4.4 Fourier series for half range, okay, I'll just give the summary of 4.4. I'm not going to go through in details because basically the whole idea of half range is basically will goes back to the even and odd function. So I'll just summarize later on 4.4.